Hello everyone. The purpose of this example is to demonstrate key concepts associated with modeling the production of biofuel precursors from algae. This two-video series describes generation of the biomass itself, equipment specifications for algae production, isolation of the key fuel precursor, energy recovery opportunities related to electricity and heat transfer agents, and economic analysis of the overall process. Before viewing these videos, it is recommended that you first watch the batch process tutorial videos as well as the continuous process tutorial videos under the training page of our website, since many of the fundamental modeling concepts for SuperPro are discussed there. These fundamentals will not be repeated in the biofuel example videos. Furthermore, please note that the files that will be discussed during these videos are part of the algal oil example that is shipped with SuperPro. That example may be opened and viewed using the evaluation version of SuperPro Designer available here. There is also a README file that comes with this example which explains certain concepts in greater detail. Additional information related to the creation and analysis of projects in SuperPro is also available in the SuperPro manual, which is included with the evaluation version of SuperPro. Let's take a look at the algae example now. Unicellular algae may be used to produce a number of different biofuel products, such as ethanol, butanol, and lipids, which can be converted into various fuels. This particular SuperPro model provides a basic representation of an algae production and purification process that generates a lipid called tripalmitin, which is a triacylglycerol abbreviated as TAG. The lipid could subsequently be converted into fuel products through a series of reactions and VLE-based separations. The SuperPro model that you see here was created by simplifying and adjusting a related model developed by Dr. Daniel Klein Markashammer at the Joint Bioenergy Institute in Emeryville, California. Dr. Klein Markashammer's original SuperPro model can be downloaded from this webpage. Dr. Klein Markashammer's model converts TAG into aviation fuel as its main product. The biodiesel example that ships with SuperPro Designer also describes a process for converting TAG into fuel. The SuperPro file associated with this example can be found in the algal oil subdirectory of the SuperPro examples directory. Note that this flowsheet is entirely in continuous mode of operation, so each unit procedure contains a single operation, and no scheduling information is specified for the operations. Furthermore, this example has been divided into 6 sections: algae ponds, algae harvesting, hexane extraction, degumming, anaerobic digestion, and cogeneration. Each of the sections in this example has been assigned a different color. The first section is devoted to the production of algae in raceway ponds, as well as the supporting nutrient and water supply infrastructure. The nutrients include phosphate and nitrate, which are fed in from raw material storage hoppers. The water is supplied from several streams, including a very large aqueous feed stream, which is recycled from the algae harvesting section back into the inlet for the raceway ponds. In addition, both seawater and groundwater are fed into the process in order to make up for evaporative losses from the ponds, as well as water losses in other downstream equipment. In this example, the algae production is modeled using a raceway pond unit procedure. The relevant algae production parameters are specified on the Reactions tab of the React operation in this unit. In this example, CO2, DAP, nitrate, sulfate, and water are consumed within the raceway ponds, and biomass, oxygen, and salts are produced. Note that the stoichiometry for the reaction must be balanced on a mass basis. Aside from that requirement, you are free to use whatever coefficients seem reasonable in order to represent the consumption and generation of materials, and which will result in an appropriate concentration of key outputs, such as biomass in this model. In this example, it is assumed that the extent of reaction is 100% of the reaction-limiting component, which is nitrate in this case. Since not all of the CO2 is consumed by the reaction, the excess CO2 is lost to the atmosphere as part of the evaporation stream leaving the raceway ponds. This stream also contains nitrogen, a small amount of nitrogen oxides, oxygen, and a large amount of water vapor. Also note that some of the CO2 involved in the reaction is produced within the cogeneration section of this model, and the remainder is produced by other utility generation units which are not included in this model. Before being bubbled into the raceway ponds, these CO2-rich streams are combined and sent through a cooler in order to reduce their temperature to 32 degrees C. Another important specification related to the raceway ponds is their physical size. Here you can see that each pond has a volume of roughly 10,000 cubic meters and a depth of 0.2 meters. Therefore, each pond has a surface area of approximately 50,000 square meters, or 5 hectares. The equipment data dialog also shows that there are 1,086 identical units represented on the flowsheet by this unit procedure icon. Consequently, the total surface area of all ponds is approximately 5,430 hectares. This is a massive surface area, equivalent to 16 times the size of New York City's Central Park, or 0.63 times the size of Manhattan. Thus, the algae production facility would need to be located in a deserted area where there is plenty of cheap land, in order for this type of project to be economically viable. In this model, the flow rate of algal biomass exiting the ponds is roughly 275,000 metric tons per year. This is based on an hourly flow rate of roughly 35 metric tons per hour and an expected annual uptime of 330 days per year. Based on these values, the aerial productivity of the ponds is approximately 50.7 metric tons per hectare per year. This is consistent with estimates from the literature regarding the current upper limit of long-term commercial productivity. It is expected that this aerial productivity limit will increase in the future as algae production systems are optimized. Note that the productivity is also influenced by a variety of factors such as location, layout of the production system, algae species, etc. The productivity is also dependent on the time of year, since this impacts the weather and the magnitude of daily solar radiation. For the sake of simplicity, in this model a constant growth rate is assumed over the course of the year. After the algae is produced, it exits the raceway ponds in stream S110 and flows to the algae harvesting section shown in blue. The purpose of this section is to concentrate the algae and then break it up in order to allow the oils to be recovered in the subsequent section. The first concentration step takes place in the clarification units, where the algae settles to the bottom of the tanks with the aid of the flocculant that was added here. The algae-rich heavy stream which exits the clarification tanks is then sent to a centrifuge, where it is further concentrated from 5% biomass to 15% biomass. The supernatant streams from the clarification and centrifuge units are combined and recycled back to the raceway ponds. Next, the biomass-rich stream is sent to the sonicators, where the algae is broken into its constituent parts in the proportions shown here. In this stoichiometric expression, NHP stands for non-hydratable phospholipids, PL stands for hydratable phospholipids, and TAG is the triacylglycerol product. Based on the relationship here, for every 100 kilograms of biomass that is disrupted in the sonicators, 26 kilograms of TAG is released and available for further processing downstream. After the algae is disrupted, the mixture is sent to the hexane extraction section shown in brown. Here, the light lipid-rich oil phase, which is almost pure TAG, is decanted and sent to the degumming section of the flowsheet for further processing. The heavy phase leaving the decanter is sent to a mixing tank and combined with hexane. The amount of hexane present in this unit is equal to 10% of the total mass within the tank. Here, the remaining oil components are extracted from the aqueous phase into the organic phase. The contents of this tank are then centrifuged in order to separate the aqueous phase and the remaining solids from the oil-rich organic phase. The separated solids and bulk aqueous phase are then sent through a protein extraction unit in order to recover proteins which can be sold as animal feed. The rest of the material exiting the protein extraction unit is sent to the anaerobic digestion section for additional processing. The oil-rich organic phase which exits the centrifuge is sent to an evaporator. Here, most of the hexane is recovered and recycled back to a storage unit for reuse within the hexane extraction tank. A small amount of additional hexane is also added in order to make up for the hexane which is lost during the hexane centrifugation and evaporation steps. Meanwhile, the oil-rich phase coming off the bottom of the evaporator and the TAG oil phase from the decanter unit are combined and sent to the degumming section for further processing. In this section, the oil-rich input stream is heated to 70 degrees Celsius using HX103 and then transferred into the citric acid addition tank. Here, citric acid is added in order to convert the non-hydratable phospholipid into hydratable phospholipid. The mixture is then cooled and sent to a wash tank where extra water is added. The material flowing out of the tank is then centrifuged in order to separate the TAG product from the other components. This results in approximately 8.3 metric tons per hour of TAG product. The TAG product could subsequently be processed into other products such as aviation fuel, naphtha, etc., through a series of reactions and separations. This example also accounts for the processing of various byproduct streams from the algae harvesting, hexane extraction, and degumming sections. These streams are sent to the anaerobic digestion section in order to convert the remaining biomass and other organic components to methane fuel. The streams are heated to 30 degrees Celsius prior to digestion in AD 701. The generated gaseous stream, which is rich in methane, is sent to the cogeneration unit. Most of the remaining aqueous material could be recycled back to the process to provide additional water and nutrients to the algae pond section. Utilities such as cooling water, steam, and electricity play a very important role in this process due to the massive scale of the facility that would be required to produce the proposed product flow rate. The cooling water demand alone is roughly 65 million metric tons per year. As a result of the extremely high utility requirements, any reduction in utility usage can have a very large financial impact. Fortunately, this process is capable of supplying some of its own utilities and raw materials within the cogeneration section. Here, methane produced in the anaerobic digester is combusted within a boiler in order to produce high-pressure steam. The CO2-rich flue gas from the boiler is sent to the algae ponds to promote algae growth, while the steam is utilized to generate electricity in a turbo generator. The electricity demand for this process can be viewed by selecting the Resource Demand chart for power. This screen shows the standard power electricity usage associated with the overall process, the individual sections, and each individual procedure within the model. To see the instantaneous power demand, I will change the Time Ref for Demand option at the bottom of this dialog to Hour. This provides the power demand in kilowatt hours per hour, or simply kilowatts. In this case, the instantaneous demand is 14,500 kilowatts, or 14.5 megawatts. The electricity production for this process may be viewed by opening the Steam Expansion Operation dialog associated with the turbo generator and selecting the Expansion Model tab. On this dialog, you can see the overall electrical power generation based on the total shaft power and the user-specified efficiency factor. In this example, the turbo generator creates 16,200 kilowatts of electrical power, which exceeds the 14,500 kilowatt demand from the process. The excess electricity produced by this process may be sold to another company or a utility. To account for the financial benefit of excess on-site electricity production, a selling price of 8 cents per kilowatt hour was established for the excess electricity production. This was accomplished by first clicking the Process Explorer button, selecting the Utility tab, and opening the standard power entry. Here you can see the purchase and selling prices for electricity within this process. These values are used by SuperPro to perform financial calculations related to energy generation. In addition to producing electricity, the 6.99 metric tons per hour of steam exiting the turbo generator may be used to meet the heating needs associated with the evaporator, the degumming heater, and the degumming wash tank, since these three units use a total of only 5.6 metric tons per hour of 152 degrees Celsius steam. To accomplish this heat recovery, a new heating agent called Steam Gen was created. The cost of this heat transfer agent was set at $0. Then, Steam Gen was selected as the heat transfer agent for the operations within units V104, HX103, and EV101. The result of these specifications is a reduction in the overall utility usage and the associated utility costs, since there is no longer any cost associated with heating these three units. Another heat recovery relationship was defined between preheater HX701 and flue gas cooler HX101. In this case, all the heat required by the Heat 1 operation within HX701 can be supplied by exchanging heat between HX101 and HX701. In addition, some of the cooling required by the Cool 1 operation within HX101 can also be met. The heat recovery between these two units was specified using SuperPro's Energy Recovery Interface, which allows you to establish relationships between various operations that produce heat, i.e. heat sources, and operations that consume heat, i.e. heat sinks. In this table, you can see all the operations within the flowsheet that require cooling. Notice that the first operation in the list has an extraordinarily high cooling load of 40 million kilocalories per hour. This operation, which cools the combustion flue gas before it enters the algae ponds, requires roughly 8,000 metric tons per hour of cooling water. Also notice that the recovered checkbox is checked for this operation, and there is a matching percent of 5.17%. This means approximately 5% of the cooling load for the P8 Cool 1 operation can be met by exchanging heat between the P8 Cool 1 operation and the P42 Heat 1 operation. The choice of P42 Heat 1 as the recipient for this excess heat was made by clicking on the View Edit button for that operation. Notice that the P42 Heat 1 operation has been selected here as the match for the Cool 1 operation in P8. Also notice that 100% of the heat required by P42 Heat 1 can be supplied by P8 Cool 1. Keep in mind that multiple heat sinks could be chosen on this dialog by selecting additional checkboxes for other operations. As a result, the excess heat that must be removed during the cool operation in procedure P8 could be used to provide heating to all the other heat recipient operations listed here. However, since we have already accounted for the heat requirements of the evaporator, degumming heater, and degumming storage tank with the steam gen utility that was described a few minutes ago, there is no need to account for their heat requirements here as well. This heat recovery dialog and the use of a pseudo-utility such as steam gen are simply two different methods that could be used to account for energy recovery. A third methodology to represent energy recovery is to actually incorporate heat exchanging unit procedures into the flowsheet itself. For more information on SuperPro Designer's energy recovery capabilities, please refer to the SuperPro manual and/or the Microsoft Word document associated with the biodiesel example file that ships with SuperPro. This concludes the process description related to the algal oil example. Please join me for part 2 of this video series, where I will describe the financial specifications and results associated with this example.